All right, everybody. So this is going to be hopefully a quick video on translations and transformations of quadratics, and it can kind of be, you could kind of use it to extrapolate to translations and transformations of functions in general, but in particular in college algebra there tends to be some emphasis on translations, transformations of quadratics. In particular, you might be given a question like this: graph f of x equals negative 2x squared minus 4x plus 4 by hand, and describe the transformations that x squared must undergo to become f of x. So I have my grid here where I'm going to graph out f of x. I also put over here, just kind of as reference, regular old, here it is, regular old x squared. So the idea is we want to be able to think about like what would have to happen to x squared for it to become f of x. So on the one hand, I guess, right, we're asked two different things. That's one thing that we're asked. The other thing that we're asked is we just need to graph this thing. So when it comes to graphing, obviously there are a few different ways. One, if you're given a quadratic in general form, you could calculate out the vertex, which is given by, it's the coordinate pair, negative b over 2a. That's the x-coordinate of the vertex. And the y-coordinate is the function value at negative b over 2a. So f of negative b over 2a. That would give you the vertex. And then you could just kind of plug in points to the left or to the right of the vertex and just plot those. And then there you go. Great. That would help you with the graphing. But as far as describing the transformations, well, I guess if you kind of understand what's going on, if you have the graph in front of you and you understand exactly what's sort of going on to translate x squared into that graph, yeah, that would work. But a better solution, what will be save you a little bit of time, and probably what your instructor will expect you to do, is to take this quadratic and rewrite it in standard form. So just as a reminder, standard form of a quadratic is a times x minus h squared plus k, where hk is the vertex and a is the stretch or shrink factor. And if you write it in this way, then it kind of gives you all of the information that you need, both to graph the function and also to explain the transformations that x squared would need to undergo to become f of x. So how do we translate from general form, which is ax squared plus bx plus c? How do we translate from general form into standard form? Well, we've got to first complete the square. And here's how I do this. So let me just rewrite the equation. So completing the square, when it comes to rewriting a function, I do it slightly differently than I would do it if I was trying to solve for x, because solving for x, if you complete the square, in order to solve for x, you have to set everything equal to 0. Here, though, we can't set everything equal to 0. Everything has to stay equal to f of x in some sort of way, because at the end we need to be able to say, okay, f of x is equal to this thing. So we have to maintain this f of x. We can't set it equal to 0. So that just means a couple of adjustments. I have another complete the square video, by the way, which if you're not familiar with completing the square, you might want to check that out. But here's how I go about it. First of all, the very first thing that we need before we can begin to complete the square is we need the coefficient on the squared term to be 1, meaning if a is not 1, which in this case it's not, it's negative 2, you need to divide through by a. So, and I'm going to divide both the left and right by a, and I'm going to write it this way: f of x over, and it's going to look a little bit funny, f of x over negative 2 equals, and now divide negative 2 out of the right hand side, becomes x squared plus 2x minus 2. Right? Just a quick check. If I distribute negative 2 into the right hand side, I get negative 2x squared minus 4x plus 4. Yeah, good to go. All right. Next, what we need to do is we need to actually start completing the square, which means we add in the b over 2 squared term. It may be helpful for you. On the one hand, I'm going to keep carrying down this left-hand side. It may be helpful for you to write at this step, to write this out. Rewrite the same thing, x squared plus 2x plus, we know that we need to add some term in to complete the square. So I'll just leave a blank there. So plus blank minus 2, bring this minus 2 down. But if we're adding in some blank, we also need to subtract that same number, because we can't just add things in willy-nilly. Essentially, if we want to add something in, the only thing that we can add in and not change this equation is adding 0. So you have to both add and subtract the same thing to not change the equation. And what do we add in here is the b over 2 term, b over 2 squared. So in this case, our b term is 2, b over 2, 2 over 2 is 1. So we're adding and subtracting 1 squared on the right-hand side. Why do we do this? Because this allows us to complete the square. This term right here, x squared plus 2x plus 1 squared, factors to x plus 1 squared. Then over here we would have minus 2 minus 1 squared, so negative 2 minus 1 is minus 3. Right? And then finally, we want all of this to be f of x equals, not f of x over negative 2 equals whatever. So we multiply through by negative 2. We get f of x equals negative 2, and leave it this way, negative 2 times x plus 1 squared plus 6. Don't expand this out and simplify it, because if you do that, you're going to end up with what we're trying to get away from. This is the form that we want. This is standard form right here. So first of all, before we do the before we graph this thing out, let's just talk about what transformations are happening. So the very first thing that I would note is that it has this negative out front, which means when you have a negative in front of the whole function, that flips the whole function over the x-axis. So first, as far as transformations go, here's my list of transformations. The very first thing is, I'll say, reflect over x-axis. And if there's a reflection over the x or y axis, those are the things that should happen, or in particular, a reflection over the x-axis, that should happen first. You don't want to shift horizontally, shift vertically, and then flip over the x-axis, because then that's just going to be all wrong. You're going to have the wrong vertex and everything. So the very first thing, if there's a negative out here, it's reflecting over the x-axis. Okay, boom, we got it. Once I've got that, now I'm going to do the, you can make your choice. You can either talk about what the 2 does, which is going to be a stretch factor. Me personally, after I've done my reflections, if they're there, next I want to start thinking about where is the vertex moving to. So this x plus 1 on the inside, when you have something that's operating directly on x like this, that's a horizontal shift. And you have to be a little bit careful with the horizontal shifts, because it's oftentimes a little bit counterintuitive. So we have this x plus 1 term. We know that this is a horizontal shift of 1, but is it a horizontal shift to the left, or is it to the right? The big mistake that people oftentimes make, and this is where it's kind of counterintuitive, is that they'll see plus 1 and they'll assume that, if I'm adding 1, that must be moving things in the positive direction. Wrong. It's not. It's the exact opposite of what your intuition expects. This plus 1 shifts everything 1 unit to the left in the negative direction. So I would say here, shift left. That's an L, by the way. That's not a 6. This isn't 6 foot, that says left. Shift left 1 unit. It's like I'm like lazy. It's like half cursive. So shift left 1 unit, right? That's what this 1 does. How about this 6 on the outside? Adding 6, what does that do? It takes everything and it moves it up 6 units. So when you're adding or subtracting something on the outside of the function, then it does work exactly how your intuition would expect. If we are adding 6, it is shifting everything up 6 units. So we shift up 6 units. This time that is a 6. Maybe I should just make that a little bit more clear and stop being so lazy about my writing. Left. L-E-F-T. Sometimes people see my L-E and it looks like a 6. Yeah, it totally does. All right, so shift left 1 unit, shift up 6 units, which this, by the way, tells us where the vertex is. This tells us that the vertex is going to be at -1, 6, which we already knew because that's built into the standard form. The vertex is at -1, 6. Okay, so we've reflected, we've shifted horizontally, we've shifted vertically. What's the very last thing that happens is this 2 out front. We already accounted for the negative. That was what we accounted for in the very first step. So we don't need to worry about that. The 2 means that everything is being stretched, vertically stretched by 2. And that's all that you need to say here. Vertical stretch by a factor of 2. If this number was less than 1, like if it was a fraction, obviously, I guess I should say the absolute value is less than 1 because -2 is less than 1. But what I'm talking about is just disregarding the negative at all. If it was like 1/2, -1/2, 1/4, whatever, if it was a fraction, we wouldn't say it's a vertical stretch. We would say it's a vertical compression. So if this was instead -1/2 times x plus 1 squared plus 6, I would have said vertical compression by a factor of 1/2. Okay? So compression just means like shrinks it. The stretch means like kind of makes it sort of more narrow. Okay. So now that we have those translations, those transformations, we could just think about what these transformations look like, but now let's instead just kind of look straight at this standard form here and see if we can graph out what what f of x looks like. So first of all, I know there's a vertex at -1, 6. So up here, -1, 6 is, yeah, about right there. Not even about, but exactly right there. Yeah, that's no approximation. The only way it's an approximation is if my tick marks are very standardized, which probably they're not. Okay, so boom, we've got that. This negative out front, this means that everything's going to be facing downwards, right? This is an upward facing parabola. -x squared would be this exact same thing, but facing downwards. So I know that this thing is going to come down. I just need to grab some points so that I can sort of graph it a little bit more accurately. And here's how I go about that. So I know it's facing down. Normally, with normal x squared, if you move, say, left or right from the vertex exactly 1 unit, how far up do you go up? What's the vertical shift? So if I move right 1 unit, then the graph moves up 1 unit, right? And that's just built into here, because if I move right 1 unit, then at 1, we're looking at what is 1 squared? Well, it's 1. If I move right 2 units, how far up do I need to go? I need to go up 2 squared, or 4 units, right? Same thing with 3. I move right 3 units, I go up 3 squared, or 9 units. So we need to figure out what is happening now, and this is where, like with our new function, this is where this -2 is going to come into play, because normally if that was just a -1, then it would be the same thing just in reverse. I would move 1 unit to the right, 1 unit down. I would move 2 units to the right, 4 units down. I would move 3 units to the right, 9 units down, right? And then it's symmetrical, so it would be the exact same thing on the left. 1 unit left, 1 unit down. 2 units left, 4 units down. But here, that 2 makes it so that rather than moving down, say, rather than moving right 2 units and down 4 units, now that vertical change is being multiplied by 2. So instead of moving 1 unit to the right and 1 unit down, I'm moving 1 unit to the right and 2 units down. And then I move 2 units to the right rather than 4 units down. It's 4 times 2, 8 units down. Let's see, so 1, 2, 3, 4, 5, 6, 7, 8. It's going to be right here. And then how about 3 units to the right? Maybe take a second, pause the video for just half of a second. If we move 3 units right, how far down are we moving on our new graph? Well, normally 3 units right would mean 9 units down, but we're multiplying all of that vertical shift by 2. So 3 units right, 9 times 2, or 18 units down. Let's see, so this is at 6. 6 minus 18 is 12, right? Am I doing my math right? So it should come down to negative 12. So here's 15, 14, 13, 12. Draw a little line here just to try to get somewhat accurate. So 1, 2, 3 units to the right, 18 units down, right here. So I have sort of the right-hand side of this parabola now. To get the left-hand side, it's just symmetrical over this, the so-called axis of symmetry, which is a vertical line going through the vertex. So this gets reflected over the axis of the axis of symmetry, and let's see. So we would just take this and move it 1 unit over to right here. Same thing here. This is 2 units to the right of the axis of symmetry, so we need to move now 2 units to the left. 1, 2 units to the left. And over here, 3 units to the right. 1, 2, 3. It's like right here-ish. Okay? And that's really like all that we need to get a pretty decent looking graph. Those, what is it? 7 points. Just try to make this as clean as possible. Oh man, all that work and then I don't make it look clean. What a waste. Try to make it look clean. This is just me being compulsive. I've given you all the information that you need. If you're gonna stop the video now, I'm not offended. Well, maybe a little bit. Try to make your graphs pretty, man. One of the things that, it sounds really silly, one of the things that sort of inspired me towards math, I had a high school instructor for honors pre-calculus and AP calculus when I was in high school. Nobody liked him. I liked him. His name was Mr. Noble. He was kind of a jerk, admittedly. Yeah, he was kind of a jerk, but I understood why he was a jerk. And at one point, I submitted some homework to him. I don't know, it might have even been like a trig homework, but I submitted some homework to him. And there were a bunch of graphs on there, and I remember, like, he was just a really hard dude to please. He was always pissed off, always grumpy about something. Most of us math teachers kind of are. But in any case, I submitted some homework to him, and when he handed it back, he handed it back to us individually, and I remember he handed it back, and then he pointed at it, and he said, "Nice graphs." And then he walked on. Dude, that was like 20 years ago, and I'm still like, yeah, that was one of my peak moments. Okie dokie. So that's translations and transformations of quadratics. It does extrapolate to other functions, the idea of the horizontal vertical translations. One thing that we didn't talk about here is horizontal compressions, which is when you have, and the reason is because with quadratics, horizontal compressions look a lot like vertical stretching. But if you're multiplying something on the inside of the function, that's a horizontal stretch or compression. So, right, there you have it. If you have any questions, let me know.